All right,
Cool.
all right. Okay. Well, let's get going finally. So, yeah, thanks for the intro, Chris. So I'm going to talk about large language models today. There's some nice little jargon here: tokenization, embeddings, transformers, and more. So we'll get into what those things mean. But first, let's see an example from a very well-known large language model. So if you've been on social media or reading news or anything like that in the last few weeks, you're probably familiar with this. This is ChatGPT, which is a chatbot that you can talk to from a startup called OpenAI. And so here I just asked it, what are you made of? And it tells me, well, I'm a computer program. I'm not made of physical matter like you, and I live on the internet, right? And you can talk to me. So you could see right away that the text is pretty good. It definitely looks like correct English, good string of sentences that make sense. So off to a good start here. So we're going to talk about the pieces of this thing. How is it doing this? How does it generate language that looks very believable, like it could have even come from a human? So first, I want to make clear what we're gonna go over today. So these are the things I hope you take away. Um, so first of all, I'm going to talk about OpenAI's GPT. So this is one language model, but it's just one. There's a whole field of large language models. There's lots of different kinds of language models. This is just the one that everyone's talking about a lot, but there's others, right? So GPT, what does GPT stand for? It's an acronym, of course. It stands for Generative Pre-trained Transformer, and we will get into all that lovely jargon shortly here. So what I hope to be able to answer for you, at least in a nutshell, at a high level, is what is GPT? What does it do? What are its goals? What are its components? How does it work end to end? So that's where we'll get into these topics: tokenization, embeddings, attention mechanisms. These are kind of the main high-level pieces of GPT. So hopefully you'll understand a little bit about what these do and how these help GPT to perform its magic. And of course, to understand that it is not magic. So hopefully this will demystify it a little bit as well. And then I'll talk a little bit at the end about how GPT is actually used in applications like ChatGPT. It's actually used in a lot of other applications. It's all over the place already. So it's usually a component. So we'll talk a little bit about that. All right. So yeah, who am I? Uh, so I am actually based on the West Coast right now. I'm in Seattle, but I have a lot of Texas connections. I spent a long time at UT Austin doing some combination of physics, math, and software for over a decade. And fun fact, actually, Chris Reed and I were roommates for a bit. So and we lived in a house together that was just full of whiteboards. Like the entire kitchen was like whiteboards. So we were probably destined to end up in tech at some point. Currently, I'm a data scientist at Microsoft, like I said, in Seattle. And I work with Azure Machine Learning. So I work on machine learning product. Um, and I get into some fun things. I mostly focus on demand forecasting, price optimization, kind of in the supply chain space generally, and then statistical decision making. So fun stuff. Good use of my background. Also, I have two kids. One is 4 and one is a year old. So I'm pretty sleepy most of the time. So if I trail off, that's probably why. Okay, a couple of things to get out of the way here. So first of all, as you might know, Microsoft is a significant partner of OpenAI. We're the developers of GPT and ChatGPT. Uh, so I'm not here on behalf of Microsoft. I'm here in a personal capacity. So important to get that out of the way. I'm not trying to sell anything. I'm not shilling Microsoft, but be aware of my potential biases. And of course, I'm not going to give any trade secrets. Not that I really know any anyway. And also that large language models aren't really my focus in the field. I've read the literature, I've read some of the code that OpenAI has put out, so I know some of the fine print, but it's not my primary area. So it's even possible there's people in the audience here who know more about this than me. So feel free to educate me if necessary. All right, now we can get into the weeds a little bit here. So I've got to give you a little bit of machine learning 101. The most important part of this, of course, is what is a model? So I tend to think of models as boxes. That's a dumb definition, but it'll suffice for us for now. So what is a model? It's a box that does something to a bunch of numbers. So in this example, I've got 5 numbers that go into the box, 2 numbers come out. The box can do lots of different things. This is just an example, right? A different box might produce a different number of numbers or might take in a different number. And if I change the numbers that go in, I probably get different numbers coming out, right? And the box, of course, does not need to be deterministic. There could be some element of randomness here. Now, of course, a model is a lot more than this. There's a lot more to talk about philosophically about what a model means. But this abstracts the concept a bit, and I think it can help to demystify what a model is for this kind of discussion. And really, for better or worse, the more time that I spend writing software in the machine learning area, the more that my mental model of a model kind of looks like this, kind of looks like a box that does some stuff to numbers. This especially can help when you're dealing with deep learning, where there's this mystical element around what the model is. It's still a box. It's really big and it has a lot of controls on it, but it's a box. Okay, so one of the more important qualities of these models is that they have parameters that you can tune. And so you can think of these as adjustable knobs on the box that probably change the output. So one set of input, one output comes out, you change the knobs, you adjust them, you probably get something different coming out, right? Fairly simple concept. So on the subject of parameters, there's this famous quote that I like a lot from the physicist, mathematician, computer scientist, all-around genius person, John von Neumann. And I think he said this in response to a colleague that had a physical model that had some tunable parameters in it. I think von Neumann was maybe being a bit denigrating about it, but he said, with 4 parameters, I can fit an elephant. With 5, I can make him wiggle his trunk. And in fact, there is such a 4-parameter function where you can fit an elephant. You can go look on this on Wikipedia if you'd like. GPT in our case has 175 billion parameters, or at least GPT-3, which is the 3rd iteration of GPT. So we can probably get a little more fine-grained than the trunk. With GPT, maybe we can get to the hair follicles. And you probably get some idea here of how von Neumann would have thought about these kinds of models. He might have been skeptical. But this is definitely how the deep learning field functions. Okay, so model training is the next concept we've got to at least chat about a little bit. So training basically means finding the best settings for the knobs or the parameters. And best is a relative concept. There are books and papers written about what best means. But this will suffice for now. And so we start with a set of example pairs of inputs and outputs. So this comes presumably from the real world. Known input, known output. We call this training data. So the idea is to adjust the parameters, adjust the knobs on the box until the outputs are close to the example outputs. And again, close is a relative and nuanced concept that has books and papers written about it. And if you spend some time learning about machine learning, a lot of your time is spent on that, actually. What does close mean? What is close enough? And then once we do that, we check how well the model predicts outputs for other examples that were not in the training data. And then probably we repeat this process if our evaluation determines that the model is not accurate enough or some other problem, right? But this is the basic procedure of machine learning and training. Okay, so now that that's out of the way, everyone's a machine learning expert. Let's actually go into GPT, what it is, what it does. So first of all, it's an acronym. G stands for generative. So it's generative in the sense that what it does is it predicts the next token in a natural language string. So you feed a natural language text string into the GPT box, and what it comes out with is a table of probabilities for, essentially every word in the language you're concerned with. So this is a very simplified example. So beware the Ides of, usually we would probably say March, if we're familiar with Shakespeare's Julius Caesar, right? Famous phrase. So GPT's probably read Shakespeare, so it probably would give something akin to this and know that March is the obvious next choice. But it's going to give probabilities for other words as well. And so you can, in a sense, you can sample from what it gives you. And you can get further text by iterating it. So if you say, okay, let's pick March, that's the most probable word coming out of here. Then you can feed it next, beware the Ides of March, and see where it goes with that. It will give you another word after that. And so this is the sense in which it's generative. It generates these probabilities of the next natural token in a string. P stands for pre-trained. So basically that just means that the box that OpenAI gives you for GPT has already been trained. They've already gone through the trouble of tuning all the parameters to get them close enough to their examples. They use a lot of training data. That's pretty key to how these things work. This is from their paper, and you can see where their training data comes from and that they're using. So we'll talk about what a token is. It's kind of like a word. So you can see the billions and billions of words that they're training on. And basically, crawl of the internet, which is terrifying. I'm hoping they're filtering it well. And also some digitized books and Wikipedia. So it's seen a lot. GPT has seen a lot. And then finally, the T stands for transformer. This is the most technical concept here. I've got a little diagram of a transformer. I believe the Google Brain people invented the transformer, and this came from their paper. A transformer is a type of deep neural network model, and they're especially popular in natural language tasks. Don't worry too much about what a deep neural network is. If you don't know already, it's a box that has a lot of knobs. I believe they're currently considered state of the art. That could be an obsolete statement in a year. Who knows? The field is moving very quickly, but this is the more popular kind of deep neural network you see here. The most important feature of this is the so-called attention mechanism. We'll talk about that later. And in fact, the diagram that I have on the right here, GPT uses a simplified version of this. They really just use the stuff on the right. They don't even bother with the stuff on the left. Okay, so I said that a model takes a bunch of numbers and makes some other numbers, but we have words. So how do we get numbers? So that's where these concepts come in. Let's talk about them. So tokenization is the first one. The basic idea is to parse your input strings into these discrete pieces, and we call them tokens. So we can assign numbers to tokens, and there's an example here on the right. This is actually from OpenAI's interactive tokenizer. So I've given it a sentence. This is a tokenized sentence. And you can see on the bottom, it's broken that up into tokens. And mostly the tokens correspond with words, but there's some interesting stuff in there, like some of them include white space, includes punctuation, and the word tokenized has actually been broken into 2 tokens. So that's pretty common, where you'll see a token corresponding with the stem of a word, and then maybe a prefix or a suffix. So kind of a word, but a little bit more. Then if you can number these tokens in your language, so you get an integer for each one. For GPT-3, we have 50,000 of them. So there's 50,000 unique tokens. We can always assign one of those numbers to them. And so here's an example with this exact sentence from GPT's tokenizer. This is the string of integers that you get out. Right. So that's nice. Now we have numbers. There's some limitations of these, though. So for instance, we can't do arithmetic with this numbering system, right? Like if you could, then you might think that the word queen might be something like the word king minus man plus woman, something like that. Right. If you apply the tokenizer from the previous slide, you get this math here, which clearly doesn't add up. Right. The numbers just don't contain any meaning about the underlying words, which is sad. That kind of limits the use. So we have to pursue some other method here to turn these tokens into numbers. And that path is embeddings. So the basic idea is to find a numerical representation that encodes word meaning. And for this, we're going to have to go to a higher dimension. So in this case, I'm showing an example where the word king is encoded into 40 different decimal numbers. And this is from an embedding model called GLOVE. GPT has its own embedding model. This is a simpler one for the purposes of demonstration. And it's color coded, so you can kind of see what the numbers mean. But yeah, if we go into this higher dimensional space, maybe we can encode nuances of word meaning, and we can determine when words are close to each other. We can do arithmetic with them. That's the hope, right? And so in this case, in fact, you can kind of do that. Here, queen really is kind of king minus man plus woman. Not exactly, but in this particular vocabulary, where there's 400,000 words, queen is actually the closest word to king minus man plus woman. So that's pretty cool. And this comes from a machine learning blog that I like quite a lot. It's really good at illustrating a lot of concepts. So definitely check that out if you're curious. So how are embeddings used in GPT? So not 40 numbers. Each token embeds into 12,000 numbers in GPT-3. So you can imagine some of the possibilities for nuance that can be encoded into 12,000 decimal numbers instead of having a single integer describing a token. This number, 12,000, is called the embedding dimension. The embeddings are actually part of the model. So the model learns the embeddings as it's learning all its other parameter settings. These account for about 640 million of the 175 billion parameters in GPT-3. So comparatively small piece, but still seems like a lot, right? And there's also embeddings by token position within a string. So you might think a token might have different meaning if it's at the beginning, the middle, or the end of a string. And so we can kind of take that into account with an extra embedding on the position. Okay, now that we've got numbers that we can do math with, we can go through GPT all the way from end to end. Okay, so this is kind of what it looks like, very simplified version, but gets at the important pieces. So first of all, the input is tokenized, and it's always a window of 2048 tokens. Even if your query is not that long, that is how long the input window is going to be that goes into GPT. So you can fill the end of it with blank tokens if you need to. So in this example, a very simple query, what are you, followed by a bunch of blank tokens. And so the first path that these tokens go into, they go into the embedding, which we just talked about. Add in a positional embedding. This is very important because now we've taken this sequence of tokens and turned it into a sequence of 12,000 dimensional vectors, right? So we are in a space now called an embedding space where we can do math on these tokens. We can do useful mathematics and come out the other side. So we turn it into we transform it to the embedding space, and then we go into the meaty part, which is the transformer layers. And we'll talk about that a little more. And then once you come out the other side of the transformers, you're still in embedding space. You've got to go back to our vocabulary space, where you're dealing with well-defined tokens. And so we can apply basically the inverse of the embedding operation. And then we can apply what's called, by the deep learning people, a softmax activation. The idea is really that we just get numbers back that we can interpret as probabilities. And those are the basic pieces. Okay, so let's zoom in a little bit. So what happens when you take an embedded sequence and pass it into this transformer layer? So in this example, I have my query, and each token is in a row of the input. And so here I'm using the row to stand in for the embedding vector. So I have four cells here, but really there's 12,000. So just think of that as being a lot bigger. And so it feeds into these layers. And so I've drawn two of them. So each box is a layer of the transformer network. So it goes in sequentially. So it goes to this first box, then it goes to the next box, and then it goes through 94 additional boxes. So input is transformed, fed into the input of the next layer. That's the idea. And there's some pieces here. There's the attention. Don't worry so much about what multi-head means. But we'll talk about attention. Then there's some other things. There's some normalization. There's something called feed forward. I'm not going to talk too much about those. They're a little technical, but they're not as interesting and maybe not as salient as attention. Okay, so let's get in a little more. What would it look like if you fed this embedded token sequence into the first layer? What does the output look like? So each layer transforms a sequence in embedding space. I keep saying that, but it's important to understand. And what that means is that we're taking these tokens that are in embedding space and doing a bunch of math to them, multiplying them by things, adding them, subtracting them. What comes out of this is the same dimension, so it's in the embedding space, but these aren't really corresponding with, each row doesn't correspond with a token anymore. It's something else. It's a fuzzed out token, right? It's no longer just a word. So I'm calling these fuzzy tokens. You could conceptualize it different ways, but think of them not quite as words, but interpolations between words. They're fuzzy. Okay, now let's talk about the attention mechanism. So particularly, we're going to talk about this yellow thing, this multi-head attention, and what it computes. So the most important thing it computes is an array called the attention. And I'll talk about this example in a minute here. Attention here refers to a degree of association between tokens in the input sequence, or fuzzy tokens, as the case may be. But on the first layer, we are talking about associations between actual tokens. The embedding vectors correspond back with precise tokens. So this is an example also from Jay Alamar's blog. So we have a sentence that's been tokenized. The animal didn't cross the street because it was too tired. And we've got the input on the left and the output on the right. And so we can look at what is the degree of association for the output from the input. And so we picked the word it, and then the colors correspond with the attention values from each other word in the sentence with the output it. And so you can see in this case, the attention unit learned to associate this pronoun it back with the subject sentence, the animal. Other layers are going to learn different things, but this can help you conceptualize what the attention really is doing. It's saying, oh, for this word, what's important to pay attention to back in the sentence is the subject of the sentence. But different layers might get very different associations there. I want to be careful about interpretation here. When we have a known input, which is precise tokens, we can visualize the output like this. But as you go further into the network in the other layers, you're really looking at associations between fuzzy tokens, not precise tokens. So these things can be hard to understand. That's a general feature of deep learning, is that they tends to be kind of a black box. So interpretation always is difficult. Okay, so what comes out of the attention unit? So we talked about the attention values, which really are an array of values. So the output that comes out, each row, is a weighted average of all the input rows. So notice that I'm not saying tokens anymore because we're fuzzified, but you kind of get the idea. We are going to take a weighted average on the first layer of all the tokens, and the weights for that weighted average are the attention, are given by the attention values. So we're going to use that measured, degree of association to weight what comes out of this unit. So we'll give less salient tokens less weight. And so in the diagram here, I've shown what the second row of the output looks like. All the other rows will be similar, except the attention values will be different. Right? We're just using one column from the attention array in this case. That's basically what it produces, though. And then the output goes in and goes into some other layers, like the feed forward network, that kind of mix things up even more. Okay, so if we come out the other side, well, we've done a whole bunch of math on these fuzzy tokens, and we're still in this weird 12,000 dimension embedding space, so we've got to get back to words somehow. And so the idea is to apply something like an inverse operation to the embedding. And then we come out, and so one way you can think about this is that a fuzzy token is kind of like a superposition of tokens. It's like exists as a sum of a bunch of different kinds of tokens. This has some nice analogies to quantum theory. Hey everyone, if you're joining us, if you're still with us, we had a little glitch in the recording during the live session. So this was recorded after the fact, just the last bit of this presentation. So there's a bit of a discontinuity here. So I'm going to be taking over from this slide. So if you experience a discontinuity there, that's the reason. So let's pick up where we left off then. So we're talking about what comes out of GPT, particularly in the transformer layers, and how we get it back into probabilities of the next tokens coming out of GPT. And so what comes out of the transformers is this list of fuzzy tokens. So they're not tokens exactly, of course. They're really superpositions of tokens, right? It's tokens that we did a bunch of math to. And so one kind of fun analogy here is that it's a little bit like quantum theory, where you talk about states as being in superpositions of other states. Like the classic example is Schrodinger's cat, right? That's in this box. And since you don't know what's happening in the box, you say it's a superposition of dead cat and alive cat states until you observe it. So it's a little bit like that, in that you have these fuzzed out tokens, and you don't know exactly which token you're going to collapse onto. You have this kind of superposition of token states going on, which is why I've called them fuzzy tokens. I'm sure you could poke holes in the analogy, but it's kind of a fun one. So the point, though, is that we do need to see how do we collapse these fuzzy tokens back onto tokens, and so you can kind of interpret the proportions, in that superposition, in each of these rows, as the probability. That's what this inverse embedding and this probability activation accomplish for you. The inverse embedding does the inverse operation of the embedding, so it takes you back into the space of tokens as opposed to the embedding space, that 12,000 dimensional embedding space. And then the probability activation just allows you to interpret those numbers as probabilities. So that's the basic idea, though, is that that's what comes out of this thing. And again, it's predicting the next token in the string, but when we use these things, we're used to supplying a query and then the bot, providing a lot of text back, a bunch of words back, not just the next token in the prompt we provided it, right? And so the way that it's doing that is it can generate the next token, and then it can iterate itself on your prompt plus the token it generated and give you the next token, right? And then it can just keep going, right? So it can kind of iterate itself. And so that's how you end up with really long responses from these models, even though they're only trained to predict the next token, or the probability of the next token. Okay, so let's talk then about what the process for training GPT looks like, just from a high level. So as you saw in the diagrams previously, it always starts from chunks of about 2,000 tokens each. So it takes all the text that it's going to train on, all those billions and billions of tokens, and it chunks those into these pieces of 2,000 tokens each. It sends each chunk into GPT, predict the token following each input token, and then it can compare its predictions that it made with the actual values from the text. And it does that using something called a loss function. So the loss function measures the degree of difference between predictions and actuals. So this is a fixture of deep learning kinds of techniques, is that you try to optimize this loss function, or you try to optimize your parameters with respect to this loss function. And so then you adjust the parameters of the model to try to reduce the loss function, right? To try to make the predictions closer to the actuals. And there's really well-known algorithms for doing this. Stochastic gradient descent is the classic one in deep learning. Won't say too much more about that, but you can always look into that if you're interested. Um, yeah, and then you just repeat this process, going through the data and optimizing these GPT parameters against the loss function until you are close enough. And close enough is a really nuanced term. There's books and papers written about what close enough means, but suffice it to say that at a certain point, you know when you should stop. Okay, so let's talk about the applications of GPT. So GPT itself is usually just seen as a building block. It's not used on its own. There's usually other structures put around it, other models put around it. It's usually fine-tuned as well for a particular domain. So what that means to fine-tune is that the base model is trained further using some data, some new training data that's from the domain that's very specific to the problem area where you're going to apply it. And this is really common, right? And so update GPT parameters via new training data. So some good examples of this are in these applications. ChatGPT, we all know about. GitHub Copilot is another one that probably a lot of people are familiar with. So that's also built off of GPT using a model called Codex that's specifically trained on code and generating code. And then Jasper AI, I'm not as familiar with, but it's a content creating API, and they're all built off of GPT models. And I know in the case of ChatGPT, we'll talk about that a little more in a minute. They have fine tuned it and they've also used it in concert with other models. And Copilot, I believe, is a fine tuning of GPT and maybe some other layers on top of it. But GPT is the base model. So let's talk about ChatGPT, since that's what everyone is really interested in these days. And the OpenAI folks have actually provided a little diagram of how they use GPT. Their blog on this is super interesting if you get a chance to look at it. So they use a couple of techniques. So first of all, they do fine tune GPT 3.5 using output from humans. So they basically have a person or a collection of people, like probably a lot of people, demonstrate the sort of output that one would want to see for certain prompts, right? So they're trying to make it more adapted to question and answering, and giving the kind of responses that a labeler would give. So they're probably building in some bias here to however these labelers like to structure information. But yeah, anyway, it's really interesting. So they have a human in the loop model here that they use. And then they do something called proximal policy optimization reinforcement learning, which is just a whole other topic that I won't get into too much now. But the point of that model is to fine tune and modify GPT a little bit more in something they call a policy model. And so the policy model is basically what gives you your answer when you query ChatGPT and ask it something. Um, they they train the policy model versus something called a reward model, and again, the reward model is trained from human input. So they actually have people rank outputs from the chatbot, say which ones are the best, which ones are the worst, and then they train this model that can rank the responses, right? And so then they can optimize the policy against that model to get out what you experience with ChatGPT. There are some other layers here that involve safety and not having it output, you know, crazy conspiracy theories and things like that. I don't know how that layer works. That's probably more proprietary, but I'm sure is also very interesting. But anyway, you get the idea of how they build off of GPT. Okay, so let's talk briefly then. This is kind of the conclusion here about what's sometimes called the bitter lesson. You have to ask who the lesson is bitter for. There's a couple of camps in AI research, and there's one that's very heavy on use of data, which is
more or less synonymous with deep learning. And then there's one that is focused much more on symbolic learning. And the first camp there, deep learning, they've really been making huge wins over the last decade, right? Deep learning has made incredible advancements. And so the bitter lesson is really more for the second camp there, the symbolic people. Um, and that is that these kinds of models, they don't start with any a priori structure, right? GPT doesn't know the structure of language. Its parameters are randomly initialized, and then it's optimized against the loss function. And so what it's learning are associations between words. It doesn't know ahead of time that there's something called subject verb order, in English. It's getting that from examples. And so that can be a little bit unsatisfying, I suppose, if you're a symbolic person. It's not the models are not structural, right? They work because they've learned from billions and billions of examples. It's actually kind of incredible how well they work, given that fairly simple assumption. Um, this brings us some pretty large drawbacks, though. The model is limited to what it sees in training. It sees a lot in training. So how much that limitation matters is kind of up for debate, but it's still true. So it can certainly reproduce biases. It can be factually inaccurate. Everybody who's used ChatGPT probably knows that. It's probably told you something that you know isn't true. It has no internal sense of morality, right? You have to engineer these things into a layer around it as best you can, and that's what the practitioners of these models do. What OpenAI has to do in order to make it safely accessible for the public. But it's pretty amazing that it can do as much as it does. It has incredible facility with language given these simple assumptions. And so the bitter lesson is that this thing doesn't. It's debatable whether it understands language or not. Right? It's just seen a lot of examples. Um, okay, so I'll mostly end there. There's some references that I have in the deck here. If you want to chase these down, if you're interested in getting a little more detail on some of the methods I described, or even reading some of the papers. OpenAI's original GPT paper is great. Google Brain's Transformer paper is seminal, is is a really interesting paper, and you can even dig into the model code for the original GPT, which OpenAI put on GitHub, which was awesome. I used that to prepare for this talk, in fact. Um, yeah, happy hacking, y'all. Um,
Cool.
then you can of course ask it, what are some good ways to end a technical presentation, right? And it gives you some reasonable responses. Yeah. So at this point, of course, you're seeing this after the fact of the live recording. If you're still watching, thanks for still watching. We had a Q&A at the time. We can't redo the Q&A, of course,
Well,
but I'll try to do.
actually, Chris, thankfully, took some notes from the Q&A.
Yeah, yeah,
I can ask you some of the questions again.
go for it.
So, one of our viewers had a question about um, hallucinations and how might hallucinations, or also known as high confidence inaccuracies, it's one of the ways people are describing it, how might those get resolved?
Yeah, right. I remember this question. Yeah, hallucinations are probably the most high profile issue I think that these chatbots have right now. And so when someone says a hallucination, I think what they generally mean is that they ask the model a question that they know the answer to, and it tells them something inaccurate. Another way this can come up is if you ask it to describe how it came to a particular prediction or a particular response, and the logic it gives you just makes no sense. Right? That can happen too. Um, so um, I'm not the best person to answer this. The practitioners in the field probably have a lot better sense for how much they think they can mitigate this problem, especially with the later iterations of the model that have been trained on more data and are probably more accurate. But given the assumptions of the way the models are built, I think you always have this problem built in. And it's really up to the way that you use humans in the loop when you fine tune these models, the layers of safety that you put around them. I think you can that's their goal anyway, to try to mitigate it. Those are the ways that they're going about it. Um, I'm sure there's always going to be holes, right? Like there's entire Reddit communities now that are dedicated to trying to get ChatGPT to say, um, morally reprehensible stuff, right?
Yeah.
So I think it's going to be a problem generally, but you can see how they're going about fixing it, right? They spend a lot of time trying to build safety layers around this thing, and using humans in the training loop to try to reduce um, its tendency to give these responses and to give more expected kinds of responses. But it's an area of active research. Um, Keep watching them, but I do think that this will always be a feature of them. At least that's my opinion.
Um, I have a I have my own question that I didn't ask in the talk, um, but
Now's your chance.
I saw I was reading some yeah talking I think it was in this Substack called Garbage Day. The guy he was making his kind of one of his darker predictions for like where AI like how we'd end up using it, and he kind of drew this diagram of like say like person on one end uses ChatGPT to generate an email and says like, "Hi, blah blah blah," like, and here's my press release, and so on. And then person on the other end receives this email, uses ChatGPT or some other kind of language model to like determine the what this email is actually trying to say, and spits out basically like their prompt.
Yeah.
um, do we I don't know. There's a question in there somewhere, uh, which is like, does it? Do we end up using this tool to just like? Does it end up? I don't know what my question is. Just
Yeah, I mean, it kind of the way that we end up using this is a pretty interesting question. It's not clear to me exactly, but it some things are becoming clear, which is that it's going to reduce the cost of generating text, right? And so the consequences of that are that anything that can reasonably be generated by this will be at some point. So things like boilerplate emails, probably a lot of kind of SEO content, um, probably a lot of articles, online that are on very, well covered topics from things like Wikipedia and books. Um, Probably a lot of marketing material, right? So
yeah.
this isn't really my area so much, but yeah, that does seem to be one of the big downsides of this is that it's going to be really hard to know if a human wrote something. I think, especially if it's copy. I mean, you can probably tell like if it's an essay from a student or something. I've even seen professors saying, "Oh yeah, we can detect it now. There's detectors for it, and they themselves can read a response and know, no, my student didn't write this. This is clearly the product of these chatbots."
Hmm.
Um, but there's definitely a dystopian side of this. Um, yeah, I don't want to comment on that too much. Other than that, I'm also worried about it. I think it's interesting. It's good to understand how these things work, because I think that can help you evaluate um, the kinds of responses you get from them. I think it's a helpful thing to know.
And like when to use it, like what?
Yeah, right, right.
um, yeah. So there will probably be it'll be kind of like a new sort of like etiquette about using it, probably like how in the past couple of decades, people people's etiquette around using smartphones has adapted. But at first, it was kind of like it was the Wild West. People used it for everything all the time in the middle of conversations. They'd pull it out to prove a point. Um,
Yeah, it's going to be interesting. It's going to be an interesting few years with this. Yeah. Oh, there was
uh,
another question that we got during the Q&A that I remember now, that was about interpretability of the models themselves. So that was a really interesting question, which is, if you get a response back from ChatGPT, or one of these chatbots, can you ask the model, why did it make that prediction? What in the model made it produce that response? And that's really interesting because this is a general problem in the deep learning field. When you build these huge, huge models that have, in this case, billions of parameters, they act essentially as black boxes, and it can be really hard to understand what's happening inside of them and why they're making the predictions that they do. And there's a whole field of research called model explainability, and interpretability, responsible AI. There's all these umbrella terms for this that are trying to tackle that problem of trying to explain how these models make the predictions that they do. But it's an open area of research, and it's a big challenge in the field right now, actually.
I mean,
So I don't have a very satisfying response for it, other than that it's a major concern of the field, and that it is still just hard to know. We really just don't know why they make the predictions they do in all cases. We can kind of hand wave at the general principle of looking at all these examples and associating words with one another through the transformer, but that doesn't tell you in a specific case why it made the decision it did.
I would wonder if that's a problem that's ever going to be solved. It seems like backtracking
There's some
billions of
there's
steps.
some interesting solutions, like in the area of computer vision. You can build things called saliency maps. Like if you have a model that can, like detect cats, in images, you can you can build a layer on top of these models that will tell you which pixels in the image, were most salient in making the decision toward whether there was a cat there or where the cat was. Right. So there's some specific problem areas where it's easier to do this than others. I think for natural language, it's probably harder, but it's not my field, so I don't want to say too much about it. I'm not even sure exactly what the field of, or what the state of the research is there.
Yeah, that's pretty fascinating. Let's see. So another question that came through was, do you say more on the relation to quantum mechanics, for example, and they were relating that back to the superposition um, metaphor you were using.
Right, right. Yeah, it's just kind of a fun analogy. I'm sure it, breaks down at a certain point. It's instructive though, in that in quantum mechanics you have states of things that don't seem like they could be mixed, like they're mutually exclusive, but you can have superpositions of them. It's kind of a statement of your uncertainty about this object. Never mind what the object actually is. But you're left with having to describe it probabilistically. And so it's kind of similar in that sense. When you work in an embedding space and you are doing a bunch of mathematical transformations within that embedding space, the objects that you are working with now are not precisely tokens anymore or words. They're in between, right? A bunch of other tokens. And so it's the analogy is kind of helpful there, especially if you come from physics. And it sounds kind of cool, but it has its limits. It's just an analogy.
Right on. All right. Well, I hear someone calling you. Um,
Yeah.
so I really appreciate your time today, and really enjoyed the talk. It really clarified a lot for me personally of what was going on, and I imagine it did for a lot of our audience as well. And look forward to getting this edited and shared.
Thanks so much, James. Really appreciate it. Thanks for taking the time.